blurb here um, about the recording. So again, welcome everyone. Like I just mentioned, we've got our website. Um, it's posted in the Discord, but it's also just, sites.google.com/view/EE book club is our website here. It's a kind of like a free domain that is just accessible on Google Drive. So actually, on that note, if anyone is kind of interested in making their own website, Google Drive does a lot of great stuff and it's pretty easy to get started. So that can be really good if you're kind of looking to build some kind of portfolio that you might want to share. Kind of like on your resume, it's always good to kind of document everything that you've done into kind of like a website. In this day and age, that usually looks good. Um, so as I was saying, on the website, we've got our schedule here. Um, this quarter we'll be going through this basic engineering circuit analysis textbook, which is available through O'Reilly. And so if you go on to this link and then you kind of just click sign in, you can sign in with your institution, and then you should be able to find Cal Poly here, and then kind of just sign in with your regular credentials. Um, and you have access to a lot of really good books. And for copyright purposes, I'm not actually supposed to be sharing the textbook itself here, so I'll try to blur blurb that out, edit that out. But anyway, so this is O'Reilly. A lot of good books here. I've got kind of like a playlist of books that I have been reading a lot. So if anyone's interested in that list, I can share it with you, but that's kind of besides the point here. So this is our schedule for the quarter, right? Last week we didn't meet. So we're now here in week two, going over kind of like the course overview, basic concepts and resistive circuits, and then you can read the rest of the schedule if you wish. It was there. So yeah, just going through this slideshow. And before I get into it, I just want to say, feel free to stop me and ask for any questions if you guys are confused about anything at any point. I'm here kind of like to support you and guide you guys through this book, hopefully. Um, but yeah, so with that, I can go ahead and get started here. So quick first thing, the course overview. I've already gone through all of this mostly. There is a link for the Discord server for anyone that is not in it already, but I think everyone here is, so that's good. Um, and then so we'll be studying circuit analysis. So this is kind of a pretty common field of set of courses that people take throughout university, right? So at Cal Poly in this quarter catalog, it actually covers EE 113, 211, and 212. So if you wanted to kind of cross-reference the current catalog and read about what's covered in those classes, you'll find that this textbook actually covers all three of these courses, right? So we're kind of zipping through about 30 weeks of material in 10 hours, right? 1 hour, actually 9 hours, right? So 1 hour for 9 weeks. So let's just do the best that we can. It is a very ambitious schedule, but I think we can get through it. At least glean some high level ideas from the book, right? You'll have your chance to sit through and cry over a bunch of example problems later on, but for now we can just get a high level idea of everything so that once you actually get to the class, you won't feel like you're drowning, which is often the case. Um, so here's just some speaker information. This is about me. My name's RJ. I know all of you guys. You guys are all great. I did drive my Prius from California to Colorado. It is now sitting at 155,000 miles. I pray every day that it doesn't break down. I know some things about electrical engineering. So I graduated Cal Poly with my bachelor's in 2021. And so that was actually in computer engineering. And I quickly found out that I don't really like programming all that much. So I kind of switched over to electrical engineering for kind of like masters. So I've been teaching Cal Poly Labs. So I've taught 151, 251. So 251 is actually the circuit theory lab for the other engineers. So thinking like mechanical, biomed. So that's usually included in their curriculum. And then 361, so that's actually the lab. So it's the electronics lab for the other engineers as well. And so yeah, I've been teaching these classes since 22, so it's been quite some time. I'm going on 4 years of industry experience. I've got two pending patent applications, so that's kind of fun. Those were just kind of pushed out to the patent offices recently. So that's actually with my previous employer, Rantec Power Systems. So I worked there for about 3 years, kind of like as their software engineer. So doing like embedded software, you can think like Arduino, but on steroids, really. And so I just started last week as a power electronics engineer, level 2, at this company called Cesium Astro. Um, so that's just about me. Um, yeah, so I updated this. So yeah, so weeks 2 to 4 will cover EE 113 material, and then 5 to 6, 211, and 7 to 10, 212, right? So we're really going at a pace of 10 weeks of material in 2 to 3 hours. So just to give you a sense of what we're trying to accomplish here. And that's just kind of like the power of reading, really, is that you can kind of learn at your own pace. I mean, all the material out there, for the most part, that you need to know is published, right? So there's nothing really stopping you from just going out and learning a bunch of material, especially because with your academic licensing, you guys have access to all kinds of really great resources that I think people don't take advantage of. And that's kind of where they lose out on the tuition, right? You think that the tuition is just for the classes that you're taking, but it's so much more. I mean, just for example, MATLAB licensing. I don't know if I had mentioned this last quarter, but so at Rantec, we were trying to acquire MATLAB licensing for just kind of like the baseline tools that they have. And so that's kind of like on the order of $50,000 a year, right? So if you can pick up MATLAB and really become proficient at it, it'll be a very valuable asset to any company that you go to. I mean, that's just for example, right? There's a lot of other things that you guys have access to, like Altium and all these like online databases. And I'll try to push those as we go along here, but I don't want to get into it too much now. So I've kind of made a little slide about my approach to reading. So before jumping into reading, you really want to kind of like look at the structure of the book and come up with a plan, right? Because if you just start reading every single word in the book, you're not going to get very far, right? There's a lot of unnecessary prose that's kind of just in there to really mark the books up and kind of make it very complete or whatever. Um, but we're technical people, right? We need to read at a very fast pace in order to keep up with the industry, right? And I mean, new things are being published every day. So if you're stuck on the basics for too long, you're not going to get very far in your career, right? So we need to make sure that we're very thoughtful about how we approach reading these large textbooks. So I took a look at the structure, of the book before jumping into it. So it's organized very nicely. Um, and so I guess some background on this book is it's actually not the book that's typically used at Cal Poly. It is a book that I dug around trying to figure out what kind of like the best circuit analysis textbook is, and I kind of found a lot of people pointing to this one. There's another one that people were pointing at, but this was, one of two that were kind of like the top good examples. Um, so anyways, So this book has learning goals, examples, and summaries in each chapter. I came up with the plan of just writing down the goals and then reading the summary, and then kind of going through and taking 1 to 2 pages of notes and really kind of making sure that you understand the examples, right? Because the examples are problems that are worked out that illustrate a lot of the key points of the right these learning goals of the chapter, right? The example problems are there for a reason. Someone put a lot of thought into writing these example problems, so it's worthwhile to at the very least, understand those, and kind of like how to go about solving some of them. Um, so yeah, I've also kind of identified some good practice problems. The book actually has these things called learning assessments throughout each chapter. Um, and so far, those are the only practice problems that I've identified, just because they actually have the solutions written right next to them. So it's easy for self-learning, right? You can actually try to work out the problem and see if you arrive at the right answer pretty easily as you go through the book. So that's kind of something I'd like to point out. All right, so we can go ahead and jump into basic concepts. Unless there are any questions, I want to kind of stop for questions here if there's anything. Nope.
What's
Right.
the
Oh,
prereq of the yeah, what's the prereq to circuit analysis? Like, can we take it by next quarter?
that is a great question. And so that's something that you would be able to see in the catalog.
Actually, I talked to an advisor today about that.
Yeah.
Um, so it EE13 113 is fall spring only,
Oh,
and then yeah, it's kind of weird. Um, and then it's physics 1, and I think it was calc 2.
there you go. Okay. So, yeah, I mean, and unfortunately, I think with the semester system coming up, I think I think William, you'd mentioned that it doesn't even like count for anything, right? Or something along the lines of that.
Yeah, like you need 2 quarters for the semester, so it's kind of not worth it anyway,
Yeah.
unless you're
So
already in it.
so that's what this is for. We're here, you know, gonna learn the material anyway, right? Who needs them? But yeah, so any other questions here before we jump into more technical diddly doos? Nope. All right. So basic concepts. This is chapter 1 of the book. Not much technical information, but here are kind of like the learning goals. So going over the system of units and kind of like standard prefixes, just defining voltage, current, and power, looking at independent and dependent sources, and then just calculating power of circuit elements using this thing called passive sign convention. So that's kind of important. I think it's a very overlooked concept and people kind of misunderstand it a lot. So we'll make sure to hammer on that part. Um, so the SI standard system is the system of units that's kind of used throughout the book. Um, this SI standard system has a lot of different units. We'll just kind of discuss the units kind of like in detail as we come across them, right? It's not really all that important to define them right at the start, but just keep in mind that we're kind of using this SI standard system. Um, so here are some standard prefixes that are used, right? So for example, we'll be looking at amps, right, or amperes a lot. And so these prefixes will come right before any of your units, right? So for example, one thing you might see a lot also is seconds, right? So like milliseconds, microseconds, and so on and so forth, right? So pico is 10 to the minus 12, nano 10 to the minus 9. I'm not going to read this out to you. You guys can read, and you guys are hopefully familiar with kind of like this engineering or these not engineering, this prefix notation at this point. Um, all right, so kind of jumping into definitions here now. So electric current is the time rate of change of charge, right? So one important point that the authors make is that electric circuits are interesting because when charges move, energy transfers, right? So this is kind of what makes these electric circuits useful in the first place, right? Is that we have little ch tiny charges moving around, supplying energy to a lot of different things, right? And um, so when there are more charged particles moving over time, there's more current, right? And so that's kind of just by definition, right? We're looking at how many charges, right? Q are moving per unit time. Um, and so current is measured in amperes, right? So that's capital A, and that's 1 coulomb per second. And so for those of you that haven't taken kind of like electromagnetism physics, a coulomb is just I don't even remember the definition of a coulomb to be completely honest. I know it's a kind of like a unit of charge. It's a ridiculous amount of charge there too. Um, but anyways, so current is a vector quantity, and hopefully those you guys have at least taken kind of like general physics where you kind of understand that vectors have magnitude and direction. If you haven't taken physics, hopefully you've at least watched Despicable Me, right? So, um, right. So we need to specify which way the current is going. And when we're looking at circuits, right, current's really only going in one of two directions. So it makes it a little bit easier for us. Um, so that's kind of good there. Right, so that's the definition of current. We're just looking at how much charge is changing per time. And then we have voltage. So voltage is a difference in energy level. And so since it's a difference, it's measured between 2 points. Um, it's very similar to gravitational force, right? We think about potential versus kinetic energy. If I pick up a ball off the surface of the Earth, I'm actually moving it through the Earth's gravitational field, right? And so voltage is actually kind of like similar in the sense that we're lifting up charges through an electric field, and that electric field is working to move the charges around. Um, so anyways, energy is measured in joules, and so voltage is measured in volts, right? So this is a joule per coulomb, right? Because we're looking at how much energy it takes to move kind of a unit charge. So I think, oops. So higher voltage kind of means like that there's a stronger voltage pushing the a stronger field pushing the charges. Right? And so you can think of that as like moving that ball up further, off the surface of the earth, right? It's very similar to gravity. It's kind of easy to think about it that way. And even when we're looking at circuits, we usually define ground to be the zero potential, right? And ground is very similar to very familiar when we're looking at gravity and lifting objects some height off of the ground, changing that potential energy. And then once you release that ball, it turns into kinetic energy, which is kind of the equivalent of current, right? So we got potential and kinetic energy, voltage and current. You can think of it that way. Oh, and so here's the differential form. Oh, differential form of voltage, right? So we got the change in work per charge there. Um, so power is defined as the rate of change of energy. So this is right. So voltage is energy per charge. We're looking at a time rate of change here. I clearly should have mentioned, right? So we're looking at how much energy is changing per time, per unit time. So dW by dt. So voltage. So since we know voltage is dW by dQ, and then current is dQ by dt, we can actually show that power, which is this, can be expressed as voltage times current, right? And so that's kind of an important point here. Um, so this is a very general expression, right? I know in last quarter we looked at Ohm's law and we could figure out, voltage for a resistor, right? And current current voltage relationship for a resistor. And so we can pretty easily find power, dissipated in a resistor by just kind of plugging it into this. But yeah, so now we're talking about independent and dependent sources. So making the statement that they're pretty self-explanatory. An independent source does not depend on anything in the circuit. De Dependent source does, right? And so these sources can supply either voltage or current, right? And they're kind of this like perfect thing here that doesn't really exist, but it makes our analysis easier. And it's a good abstraction, at least to get a first cut at trying to understand what's going on in a circuit. Oh, and here's my very professionally drawn in Microsoft Paint pictures of these independent sources. So a voltage source here on the left will have a plus and a minus terminal. And then the current source will have an arrow. Um, and so this independent voltage source will supply whatever voltage is prescribed, regardless of how much current is going through it. And then, the independent current source will supply the prescribed amount of current. And so, like I said, this is a gross abstraction. These do not exist in nature, but it makes our lives easy. Um, so when we're looking at circuit elements, we like to talk about their current voltage characteristics. And so here I've drawn them out for these independent sources, right? So for the voltage source, we can see that no matter what current, and this is supposed to be a straight line, it was as straight as my hand could draw it. So regardless of what current is appearing, the voltage is staying the same for this voltage source. And for this current source, regardless of what the voltage is, the current is fixed, right? So that's kind of what these current voltage characteristics look like. Um, and it's pretty easy to see that, why these don't exist in nature, right? Because this would imply that I could just have, an arbitrarily large amount of current, right? I could just have like infinite current. And so you can't do that, unfortunately. But if you can figure out how to do that, you might get a cool prize. But yeah, so that's that. Then we got these dependent sources. So these are just symbolized with the diamond. Sometimes you'll see them in a square in some textbooks, but just definitely not a circle. And so these just supply. Oh, and I forgot to update this, so let me change that real quick. So I'm just going to completely delete these. All right. So yeah, these dependent sources will have some kind of expression attached to them that kind of like depend on some other part of the circuit. And so you'll need to keep that in mind when you're doing analysis. So we won't get into it too much right now, but just something to keep in mind. Um, and so I think this is the last point here. So yeah, the passive sign convention is used to consistently analyze power. And so, like I had mentioned, this is kind of like one of the most misunderstood topics, I think, just because it's kind of weird when you think about power being positive or negative, right? But so we're using this passive sign convention um, to analyze power, and we kind of use um, these directions, right? So we have voltage, we always have the current going into the positive terminal, right? The higher potential of an element, right? And so this way we can define the power to be positive if this is happening. And so when we say the power is positive, that means that this element is actually absorbing power. And so if it turns out that once you go through your analysis that the current is actually entering the negative terminal, right? This lower potential, then the power is actually negative, right? And so that just means that the element that we're looking at is actually supplying power, right? So if I go through my analysis and I figure out, that this element is actually doing something like this, right? Where I have V. And so if current is negative, right, we just flip the direction, right? So it's actually ends up going this way. And when we have something like this, when the current is leaving the higher potential of an element, then this element is actually supplying power to the rest of your circuit. Um, and so it might make more sense once you go through some examples, but that's kind of what this passive sign convention is. It's just when we're looking at power, we're always thinking about the current going into the positive, the higher potential of an element, right? And so that's that. So unless there are any questions, I do want to walk through some examples here. Um, and to do so, I'm actually going to share my iPad screen, hopefully, if this works. Oh, cool. That was a lot easier than I thought it was. So can everyone see this iPad screen? Yeah, good. All right, cool. So let me just double check what problems we wanted to go through. So kind of like the first one I wanted to do is example 1.2. Um, we'll just walk through some of these just so that everyone kind of is on the same page with these ideas here. So, and I wish I wish I could just share the textbook, but for obvious copyright reasons, and I'm hoping to put this on YouTube. We can't actually just do that, but I can draw it out, I think. So example 1.2, we're looking at this really strange circuit where we have 4 amps and we have some amount of voltage, and we're asked to determine whether the element is absorbing or supplying power and how much. And so when I look at this, I instantly see that the current is going through the negative potential, right? So this lower potential right here of that element. So this element is supplying power. And another way to do that using, what we had just learned and the whole idea of the um, passive sign convention, right? Um, we can actually solve the power. And so this is always I times V. And by the passive sign convention, since this current is going into the negative, the lower potential there, the current is actually negative. So I have negative 4 amps. And then I always have just a positive voltage, right? So this is minus 8 watts. Um, right. And so by the passive sign convention, this element is supplying power because power is less than 0, right? So there's that. Um, as a secondary example, they have this circuit. So there's some other blob there. And then they have an element, and they have this current which is actually defined to be negative, and then they have this voltage. Right, and so whenever I have negative current, it's actually going in the other direction, right? So I could just redraw it just to make just so that everyone's on the same page here. So I actually have this circuit. And so just like the previous example, I have the current coming out of the positive potential, right? So actually back here, I had it going in to the negative potential, right? This lower potential, but it's actually also coming out of the positive potential, right? Because it can only traverse, through that path there, right? So it's going in, what goes in must come out. It's also coming out of the positive potential. Just like here, it's also coming out of the positive potential, right? So by the passive sign convention, I have P, which is I times V, which is -2, right? Because I'm actually entering the negative terminal. So -2 amps times my 2 volts, and that gives us -4 watts. So the element is supplying power again. All right.
Would there be a case when the voltage is negative?
Yeah, and so that's actually a good point. And um, that was part of the learning assessment problem here. Um, but we can talk about it here. That's a great question. So when the voltage is negative, right? So let's just say I had something like this, right? So maybe I have, let's say I have something like that, right? So if the voltage is negative, we're actually just swapping the potentials, right? So um, that circuit is equivalent to this. I just have 2 volts, but swap the potentials, right? And you could proceed with the analysis just as we had done before, right? So I'm going into the negative terminal. So by the passive sign convention, this current is actually negative. So -2 amps times 2 volts. So I get this -4 watts again. Um, but yeah, so generally speaking, when you have negative current, the current's going the other way. And when you have negative voltage, you've got the potentials swapped. Um, okay, so that's 1.2. And next I wanted to do 1.3. And so for this example, we have this circuit. So they've labeled the nodes here as A and B. We've got 5 amps. We're not sure what this voltage is. And we're given that the power here is -20 watts. Oops. -20 watts. So if that's -20 watts, then I know that this current is entering the lower potential, right? So we know that much. And we know that power is I times V, and we know that I is 5 amps. So we can actually solve for V. V is P divided by I. And so we know that this is 20 divided by 5. So that gives us 4 volts. Um, right. And so I kind of just neglected the sign here because I already determined where the potential is, right? So how to mark up the potential there. Um, so I know that the circuit that we actually have, is just like this. So minus plus 4 volts. And then here's my element. And there's my current. And hopefully that's consistent with what they did. Yes, okay. All right. Cool. I do know what I'm doing. Um, all right, anyways. So there is a part B of that example, but in the interest of time, saying that we only have 15 more minutes really, or 17 minutes here, and I wanted to go through an entire other chapter. Let's just jump to the next example. So for this next example, unless there are any questions there, feel free to shout out, as we're going through these. So example 1.4. So we're looking at something like this. They've numbered the elements this time, and we've got 24 volts. Um, we've got 6 volts across that element, 18 volts across the second element, um, 2 amps here, 2 amps there, and 2 amps here. 2 amps all over the place. And we'll get to why that is in a moment, but so here we're trying to determine the power absorbed or supplied by the elements in this network. Um, so I'm going to call this power the source. And we can see that it is entering the lower potential, right? So I've got a minus 2 amps times 24 volts. And so that's minus 48 watts. So this source is supplying power as we would hope. Um, for the next element, so we call that P1. So I'm going into the positive terminal this time, which means that my current is actually positive. And I've got 6-volt drop across it, so that's 12 watts of power. And then for P2, I've got 2 amps going into the positive terminal and going down 18 volts. And so that gives me 36 watts. And yeah, so that's all that they wanted for that example. Pretty straightforward, right? So we haven't really hit anything overly complicated, hopefully, yet. And actually, circuit analysis is, it's not too complicated once you get into it. You kind of just need to go through example problems kind of consistently, and it's good practice for me too, right? Because I don't actually do all that much circuit analysis. It's a lot of simulation tools on the job, but it is helpful um, to make sense of what you're doing, right? To kind of as a sanity check, look back and think, okay, yeah, that simulation does make sense, right? So anyways, unless there are any questions on that, we can jump into resistive circuits here, kind of like the next chapter of the book. Cool. All right, no questions. So let's jump
Oh, I have a
back.
question real quick.
Oh yeah, go ahead.
Um, are you gonna post the slides on Discord or something?
Oh yeah, I completely forgot to do that. I will generally try to do that um, before each meeting,
All
and
right.
I will do that for this as well.
Okay. Perfect.
Um, yeah, so you guys can see the slides now, right? Yeah, we're good. Cool. Um, all right, so jumping into resistive circuits. So here are the learning goals, right? So we're going to learn how to use Ohm's law. That should hopefully be review for most of you. We're looking at Kirchhoff's current law and Kirchhoff's voltage law, looking at single loop and single node pair circuits, talking a little bit about voltage and current division, and then understand how and why, when and how to apply Y delta transformations, and then know how to analyze circuits containing dependent sources. Um,
You're
all
sharing
right.
your iPad.
Oh, hilarious. Thank you. that should not be happening. Is that the screen now? Yeah, that is. All right. Okay. All right. Here are the learning goals. I just read them off for you guys, so I'm not going to go through them again. Um, all right. Ohm's law. So Ohm's law states that the voltage across a resistance is proportional to the current flowing through it. This should be this should definitely be reviewed for everyone. I'd imagine Derrickson's section at least covered Ohm's law. Am I right in that, Rizana? You guys cover Ohm's law? No. All right, I'll just keep going. All right, so um, resistance is measured in ohms, right? Like I'd mentioned before, we'll be going through the SI units as we encounter them. So this is measured in ohms, and 1 ohm, as I've got written out here, is actually just 1 volt per amp. Um, so by Ohm's law, we have some voltage is equal to the product of resistance times current. And so both voltage and current in this regard are now considered time varying, right? These are now functions of time. Resistance is not a function of time in this case, right? In the real world, it kind of is. Resistance isn't like a perfect fixed value. Um, but anyways, for the sake of analysis, we're assuming that the resistance is just some beautiful constant value that is unchanging. Um, and it's also kind of important to note that we have the definition of conductance here in the text as well. So conductance is just the reciprocal of resistance, right? So when something is more resistive, it is less conductive. Something's more conductive, it's less resistive, right? And just something to keep in mind. Some people analyze circuits using conductance, right? Just because it makes it easier for some things. But for the most part, we'll be looking at resistance. And so next we are moving on to Kirchhoff's current law. So the Kirchhoff's current law states that the algebraic sum of currents entering any node is 0. Um, and so we had kind of looked at that last quarter to some extent, but if I guess we hadn't formally defined what a node is yet. So a node is kind of just a connection of two or more circuit elements, right? And so whenever we have a bunch of different connections, um, we can at least say that the current going into that connection is equal to the current going out of it. And that's just by Kirchhoff's current law. And so I've got it written out here as a sum, right? This is a discrete sum symbol. And so if I have a set of currents, I1, I sub 1 to I sub n for however many elements you have connected into that node, right? So if I sum the currents, then that should be 0. All right, so Kirchhoff's voltage law states that the algebraic sum of voltages around any loop is 0, right? And so I forgot to mention this, but Kirchhoff's current law is kind of like what goes in must come out. Kirchhoff's voltage law is like what goes up must come down, right? So these are kind of universal truths almost. Um, so then in order to really analyze Kirchhoff's voltage law, we kind of need to define what a loop is. And so a loop is just any closed path through the circuit, right? So you should be able to kind of like trace your finger around in a loop without any breaks really. Just go from one node back to itself, and that constitutes a loop. All right, so now we're kind of looking at these single loop circuits. Right, and so the text does this interesting thing of defining single loop and single node pair circuits, which I actually haven't seen in any other textbooks. Christian, I don't know if you're here, but have you have you come across this like single loop circuit definition? There's like a whole section of the book on this. Kind of interesting. Um, but anyway, so the single loop circuit is just, a set of elements that are really connected in series. We say that they're in series, right? Because there's only one path for us to traverse here, right? So if I start, for example, up at the top left here, and I try to traverse through the circuit, right? I've only got one path to go. I go through this element, I go through this element, come back, go through the source, right? There's only one path there. And so this is a single loop circuit, and it's one of the most, it's one of the most basic closed circuits that we can really look at. So right, all of these elements will have the same current, right? So whenever we look at an element, current in must equal to the current out, and that's also the same. That's also true of these nodes, right? So I've got a node here, so the current into that node must equal the current coming out of the node, right? So once I've gone in, come out through the voltage source, gone into this, I also have to go out through the resistor, right? So what goes in must come out. I've only got one path for current to flow. Current is the same in each of these elements there. Um, so typically, in order to solve this kind of circuit, we would define the voltage across each resistor, in terms of the defined current direction. And we usually make the assumption that each of these resistors are passive elements, right? So, for example, since I've defined the current going this way, in order for R1 to be passive, I want the current to be entering the higher potential. So that's my V1. This is my V2. And so these are both passive. And then we'll get into this a little bit more, but the sum V1 plus V2 must equal VS, right? Because if I start here, for example, and I take this path, I go up VS, right? So up here, I'm at VS. And then if I traverse through this path, I go up V2, I go up V1, and I arrive at this VS, right? So this is actually equal to V1 plus V2. But anyways, so that's a single loop circuit. Um, it'll make a little bit more sense if we can even get through examples here. So each element in a single node pair circuit has the same voltage across it, right? So if we kind of just consider KVL here, what goes up must come down. So if I'm going up through the source, I must go down through the resistor, right? So these voltages are actually equal. And, if I look at this outer loop, the same is true, right? If I'm going up through the source and I go through this element, going down through there's R2 here, right? So the voltage across the source is the same as the voltage across R2. And so all of these voltages are equal, and we say that they're connected in parallel, right? They're in between the same two nodes here, right? So here's my top node. This is just the node is the interconnection of all the elements, and this is my bottom node, right? So since they're all in parallel, they all have the same voltage across them. And so the book actually has kind of like an algorithm for solving both the single node pair and the single loop circuits, right? It's kind of labeled as this. Let me see if I can find it or what they call it here, but you can flip through the book. Yeah, so they call it. There's a section called problem solving strategy, and so they have one for the single loop circuits and for the single node pair circuits, and this is kind of where I derived, this set of bullet points from. So it's worthwhile to go through the book and kind of look at those. Um, So the general principle is, since we know the voltage, we want to use KVL, right? Or KCL, because we want to determine all the currents. Because we know the voltage is the same, so we can exploit that to just use KCL and solve for the circuit. Um, and so kind of like the opposite is true for the single loop circuit. And I forgot to mention this. Right? We know that all the currents are the same, so we can exploit KVL to kind of solve for the circuit, right? We write KVL equations to solve the circuit for this situation. Um, and so we'll go through some examples. Maybe next time. I don't want to, I want to be um, consistent. I want to be consistent with the scheduled time that I had allotted here for everyone. So I'll try to crank through, these learning goals at the very least. And then maybe next session we can go through some examples and try to speed up the process here. All right, so next for the next kind of like learning goal, we're looking at voltage division and current division. But first, we're looking at voltage division here. So when we apply a voltage source to, just a simple network of two resistors, I immediately see what's called a voltage divider structure, right? And so what's happening is the voltage gets divided between these two resistors in proportion to how much resistance each resistance has, I guess. And we looked at that very loosely in some of our projects last quarter. But it comes up again and again as you proceed through your career. It's all over the place. These voltage dividers are very important circuits. But basically, more resistance means greater voltage drop, and the voltage can only, it has to sum to the source, right? We can't just have more voltage across these resistive elements as it's being supplied, right? Because again, the source is really the only thing that's capable of supplying any kind of power. These resistors will be absorbing power. Um, and so you'll get to an interesting case, maybe in your electronic design, where you'll have circuits that, are set up in a way that it looks like the resistors are actually supplying power. And Christian probably came across this last quarter in his 409 class. But obviously, resistors on their own can't supply power, right? There has to be some kind of op-amp structure that's actually pumping energy through the resistor or something, right? It's got to come from somewhere. So generally speaking, resistors cannot supply power. And so when we have this voltage divider structure, if we sum the voltage drops across the resistances, um, it'll equal the voltage of the source. So that's kind of important takeaway there. All right, so next we kind of have this current divider structure. And so I'd say that this is less common. I don't come across current dividers all that much. But it is kind of covered very frequently in kind of like circuit analysis texts. So it's something to keep in mind, right? So this current divider, we look at, the current source, and then we have a network of two resistors in parallel. Um, and so generally speaking, more resistance means less current, right? So one easy way to think about that is through kind of like the definition of conductance. That's kind of like how I like to think about it. When something has less resistance, it's more conductive. And so that more conductive path will obviously see more of the current, right? It's conducting more current. So whenever you see a structure like this, you kind of just want to think, okay, whichever one has less resistance is going to have more current through it. Obviously, each of these will have the same voltage across them as we had discussed before. But there are a bunch of fancy equations that kind of you can use to solve the voltage divider and the current divider, and we'll look at the examples of kind of how to do that in the next section there. But next, so there's also these transformations, right? So it's kind of interesting that in the set of learning goals, there isn't any kind of discussion of series resistance combinations or parallel resistance combinations. Um, but there are, equations for that are very handy in the analysis of circuits. So I think that's one criticism, yeah, one criticism I'd make of this book is that I think um, adding resistors in series or adding resistances in series and in parallel is kind of an important learning goal that I'd say would come before these Y and delta combinations. But one could probably argue that um, it's kind of like baked into these single loop pair and single node pair circuits, but I don't know. Kind of interesting. So, anyways, um, we have Y and delta connections. And so these are a little bit different, right? So when we're looking at resistance in parallel and series, we're usually looking at an arbitrarily large number of elements. Um, but for these Y and delta connections, there's actually three, right? So it's a fixed number of elements in these structures. And we can actually transform one to the other, right? So this is a delta structure, right? And you'll note that all of these nodes must be consistent, right? So there are equations relating each resistance, right, in the transformation, and you need to be cognizant of where these nodes are and where these resistances are. Um, right, this is the delta structure. It can also, you know, be drawn differently, right? So this like triangle thing is actually topologically equivalent to, maybe something like this. I don't know, right? Where this is maybe this is A, and so this is R2, and then this is B, this is R3. Wait a second, what did I do? A, and then go through R2, and B, go through R3, it's C. Yeah, so there you go. And then this is R1. Right, so this is topologically equivalent. And so that's one thing also, um, is kind of just being able to look at a circuit regardless of how it's drawn out and kind of understand the connections. But I think that's one big thing that people struggle with as well. Um, but anyways, that's also besides the point. So as I was saying, you want to be careful with where these nodes are, and then also the definition of how to make this transformation. And so in the textbook, there's also kind of the opposite transformation, right? So uh, this is from delta to Y, right? So if I have delta, if I have R1, R2, and R3, I can figure out RA, which is, the product of R1 and R2 divided by the sum of all three, right? And so on and so forth. The textbook also has the inverse transformation, right? Where if we're given our A, B, and C, we can calculate R1, R2, and R3. But you won't, I don't think you'll come across this all that much. And even if you do, you'll typically just be able to look up the transformation and it should be pretty straightforward. Oh, that stayed on there. And so the last learning goal was just kind of analyzing circuits containing dependent sources. So that's pretty straightforward. You would approach it the same way as you would just a dependent or sorry, an independent source. Um, and you would kind of just solve the system of equations that you end up with algebraically. And obviously we can get into all of that in the next meeting when we go over some more examples for this stuff. Um, but as I was saying, I want to make sure that everyone gets their 8 hours of sleep here, so I don't want to keep you guys for too long. So I'll stop the recording here, and then if anyone has any questions on anything, I am happy to